Hey everyone, and welcome to The Explainer. Today, we are going on a truly fascinating journey. We're going to zoom way out from the basics of everyday movement, the stuff we can readily see and touch, and dive into the elegant, three-dimensional math that invisibly rules our physical world. By the end of our time together, you're going to see the hidden forces around you in a completely new light and understand exactly how the universe accounts for every single drop of energy. All right, let's dive right in by anchoring ourselves in reality for a second. Picture this. A massively heavy rock resting precariously right on the very edge of a towering cliff. It's completely, totally still. Now, picture a fast-moving car zipping along the highway down below. So, what's the fundamental difference in their energy? Well, one object, that teetering rock, has a massive amount of energy stored entirely by its position, literally just waiting for a strong breeze to unleash it. The other object, the car, possesses energy strictly through the fact that it's currently in motion. So here's the breakdown of those two primary forms of energy that dictate mechanics. First, you've got kinetic energy. Exactly like that speeding car, this is the energy an object has inherently because of its motion. If you look at the math, it depends entirely on velocity and mass, 1/2 mv squared. But then you have potential energy, like our precarious rock, which is completely independent of motion. It's purely stored energy, based strictly on the object's height, its mass, and the constant pull of gravity. As long as that rock just sits there, its energy is pure, unadulterated potential. It's basically building up an energy bank account based solely on where it is. So here is our roadmap for today. We've got 5 steps. 1, the basics of energy. 2, the work energy theorem. 3, understanding force fields. 4, calculating work in 3D. And finally, 5, secrets of conservative forces. We're going to start with familiar high school definitions of energy and build a bridge step by step all the way into university-level multivariable calculus. It's going to be a great ride. Starting us off with part 1, the basics of energy, the foundation of mechanics. Let's get our groundwork laid out before things get mathematically complex. Basically, everything in mechanics eventually ties back to this single, beautiful concept, the work energy theorem. The theorem simply states that the net work done by all forces acting on an object is equal to the change in its kinetic energy. Look at that core equation. W net equals Kf minus Ki. That just means the total cumulative work is exactly equal to the final kinetic energy minus the initial kinetic energy. It's the vital bridge connecting the physical forces applied to an object, like pushing a heavy box or slamming on your car brakes, to the literal change in its speed. It perfectly connects cause and effect. Moving right along to section 2, the work energy theorem. Applying the concepts, let's actually put this theorem to use in the real world. Here is the absolute kicker. This simple toolkit allows you to solve highly complex mechanics problems without even needing to know the time of travel or the exact acceleration. It's incredibly elegant. First, you identify your system. Second, note all the external forces acting on it. And yes, definitely include tricky things like friction. Third, calculate the work done by each individual force. Fourth, find your initial and final kinetic energies. And finally, just apply that W net equals Kf minus Ki formula. It's a hugely powerful shortcut for physicists that cuts right through all the messy details of time and distance. Let's put some real numbers to this to give you some perspective. Applying the theorem tells us that exactly 900 joules of work is done by a tiny 20-gram bullet as it slows from 500 meters per second down to 400 meters per second. Think about that for a second. Just by knowing that minuscule mass and the exact change in velocity, we can reliably determine the precise amount of work the environment had to do to slow that bullet down. 900 joules. We don't need to know what material it hit. We don't need to know how long it took. The energy difference literally tells the whole story.
Okay, section 3, understanding force fields, forces in 3D space. Let's see how this builds when the force changes as you move dynamically through space.
In a standard introductory math setup, vectors just have direction and length. Because of this, we can kind of lazily originate them all from a single 0 point, like a neat 0, 0, 0 origin. It makes the math tidy, it's easy to graph, and it's super simple to digest. But physical reality is way messier and demands a lot more nuance than a neat little graph. Step into the real world, and a true force field is wildly dynamic. The gravitational pull on an object completely changes depending on its specific three-dimensional location in space. A vector at one position is fundamentally different from a vector at another because it's reacting to different masses, different distances, and different bodies. Every single coordinate you can plot has its own unique specific force vector. You aren't just dealing with a single push or pull anymore. You're dealing with an entire ocean of forces that constantly shift around you as you move through them. Which brings us to Section 4, calculating work in 3D, navigating 3D forces. So, if our force is constantly shifting depending on exactly where we are, how on earth do we actually calculate the work being done? Well, enter the Riemann definition of a line integral. It sounds intimidating, but honestly, it brilliantly solves our problem. It tells us not to panic about the overwhelming complexity of a whole winding curve, but rather to just chop that path up into infinitesimally small, linear segments, what physicists call dr. Instead of one giant calculation, we calculate the force at one exact microscopic point, multiply it by the tiny dr step, and then simply add up all those microscopic steps along the entire journey. By breaking an impossible curving path down into billions of tiny straight lines, the math suddenly becomes entirely solvable. To actually solve this in practice, physicists use parameterization, mapping that incredibly complex 3D curve into a single manageable variable. And why does this dense calculus matter to us? Because it gives us the exact tool we need to calculate insanely complex real-world events, like, say, the massive cosmic work Earth's gravity performs on a passing meteor. Without line integrals, we simply couldn't accurately calculate the energy of objects moving through the violently shifting gravitational fields of our vast solar system. This is literally the math that helps us understand the cosmos. And that brings us to our final stop, Section 5, Secrets of Conservative Forces, Path Independence. This is the most elegant concept in mechanics, where the math loops perfectly back around to where we started today. If a force field is what we call conservative, it literally does not care how you get from point A to point B. The work done between 2 points is absolutely identical regardless of the path you take. Whether you take a straight, direct route or a wildly winding, chaotic detour, the total work done by the force field is exactly the same by the time you reach the destination. Gravity is a perfect example of this path independence. It doesn't care if you took the scenic route, it only cares about your starting altitude and your ending altitude. Because of that, if you take a journey through a conservative force field and end up exactly where you started, forming a perfectly closed loop, the total net work done by that field is precisely 0. The work done moving against the force perfectly cancels out the work done moving with it. If you climb all the way up a mountain and hike right back down to your car, gravity's total net work on you is 0. It's a perfect mathematical balance. So let's stack these two big ideas side by side. The work-energy theorem we looked at earlier is universal. It accounts for all forces, including lost energy, like the friction heavily heating up the brakes on a stopping car. Friction is non-conservative because that heat energy is lost to the environment. You can't get it back just by reversing your path. Whereas the conservation of mechanical energy strictly applies only to these perfectly path-independent, ideal conservative forces, where energy simply transforms beautifully back and forth between potential and kinetic without a single drop ever being lost to the void. Now, physicists don't just blindly guess if a force is conservative, they've rigorously prove it. They use Stokes' theorem to prove it by showing that the curl of the force field is mathematically 0 everywhere on a given surface. Think of curl as a measure of whether the field has a tendency to rotate or swirl, kind of like water going down a drain. If the curl is completely 0 everywhere, there's no hidden swirl to mess up our math. They know for an absolute fact that the closed loop work is 0 and the force is perfectly conservative. And wow, does this bring our entire journey full circle. F equals negative del U. The force is equal to the negative gradient of the potential energy. This advanced multivariable equation proves that conservative forces are simply the physical manifestation of the potential energy we discussed at the very beginning of this explainer. What does that actually mean? Well, a gradient just points uphill to higher values, so a negative gradient points strictly downhill. The force is literally just the universe trying to roll objects toward a lower state of potential energy, exactly like our rock wanting to fall off the cliff. So we've gone all the way from rocks teetering on a cliff to multivariable gradients and cosmic force fields. Whether it's the friction slowing you down on your commute or the immense potential energy waiting to be unleashed in the world around you, the mechanics of the universe are constantly at play in your life. If energy is never truly lost, only transferred, what forces are shaping your path today? Keep exploring, keep questioning the mechanics of your world, and I'll see you in the next explainer.